This is the 4.4 and 4.7 review. Calculators still are not allowed, and this is number 3, where again we are computing limits. So chances are good that because we're computing limits and we're dealing with chapter or section 4.4, this will be a L'Hopital's or some sort of indeterminate form. And indeed, if we plug in 0 here, we'll get a 1 divided by 0, which is going to be asymptotic in behavior, so that will be heading toward infinity or negative infinity. And if we plug a 0 in here, we will have a log natural of 1, which is 0. So in this case, we're getting an infinity times 0, which is an indeterminate form. Same thing here, I'll have a 0 times the cosecant of 0. That's the reciprocal of the sine of 0, so again that will be 1 over 0, which is an asymptotic sort of behavior, which will be infinity. Third one here, we plug in pi over 2, we'll have a 0 times the 1 over the cosine of 0, or excuse me, cosine of pi over 2, which is 0, so asymptotic again. So all three of them are these 0 times infinity sorts of indeterminate forms. So if you recall, how we work with these is we create 0 over zeros or infinity over infinities by rewriting the term here, the expression. We rewrite it as a fraction. So if we look at A, it's pretty easy to see that we could make a single fraction if we just put this 2t on the bottom. So we can rewrite this as the limit as t approaches 0 of the log natural. And I'm going to rewrite this as a 1 plus a 1/3 t, because I'm kind of looking ahead to the fact that I'm going to have to take the derivative. And on the bottom, I'll have a 2t. Now if I plug in 0, I will get a 0 over 0, which is eligible for L'Hopital's. L'Hopital says I can just take the derivative of the top and the derivative of the bottom and then compute the limit. So the derivative of the top is 1 over that inside times the derivative of the inside, while the derivative of the bottom is just 2. If I now plug in 0, I'll get a 1 times a 1/3 divided by a 2, which is a 1/3 times a 1/2, or a 1/6. If we look at part B, this one is not quite so obvious. With part B, I need to create a fraction. So I can create a fraction by either putting the reciprocal of x squared minus 1 on the bottom, or by putting the reciprocal of cosecant on the bottom. Well, the reciprocal of cosecant is sine, and I would actually rather work with a sine than with the cosecant. So that's the choice I'm going to make. I'm going to leave the x squared minus 1 on top, and I'm going to rewrite cosecant as 1 over the sine of that x squared minus 1. So now when I plug in 1, I'll get a 0 over the sine of 0, which is 0. 0 over 0 is the indeterminate form that I can apply L'Hopital's to, which I will do. Take the derivative of the top and the derivative of the bottom. Don't forget your chain rule. The two x's will cancel, and I'll get a 1 over the cosine of 0, which is 1 over 1, or 1. Last part, C. I again have the same scenario I did with part B. It's not real obvious what should go on the top and what should go on the bottom, but I'm going to choose to put the reciprocal of the secant, which is a cosine. I'd rather work with a cosine than a secant, so I'm going to put the reciprocal of that secant on the bottom of my fraction. So that'll be the limit as x approaches a pi over 2. On top, I have an x minus a pi over 2. And on the bottom, I'll have the cosine of pi over 2, or x, which means when I plug in my pi over 2, I'll get a 0 over 0, which means it's a candidate for L'Hopital's. Now I can take the derivative of the top and the derivative of the bottom. So derivative of the top gives me 1, derivative of the bottom gives me a negative sign. And now if I plug in pi over 2, the opposite of the sine of pi over 2 is negative 1, so I end up with a limit of negative 1.